Nvidia did not win the AI era by building the fastest chip. It won by building something competitors couldn't copy in a single product cycle. A software world that millions of developers already depended on. To understand how that happened, you have to go back to a time when nobody thought of Nvidia as an AI company at all. Go back to the early 2000s. Graphics cards were built to do one thing: render pictures for games. A GPU could push millions of triangles onto a screen every second, filling them with light, shadow, and texture in real time. That took an enormous amount of parallel arithmetic, thousands of small calculations happening simultaneously. But that raw parallel power was locked inside a narrow pipeline. Meant only for graphics. You could feed it triangles and textures. You couldn't feed it, say, a weather simulation or a stock market model, because the hardware had no general-purpose doorway in. Researchers noticed something strange anyway. The same chip that rendered explosions in a shooter game was mathematically extremely good at another job entirely: crunching huge grids of numbers at once, physics simulations, matrix math, early neural networks, which are underneath all the terminology, mostly just enormous amounts of matrix multiplication. The hardware for general computation was sitting right there inside millions of gaming PCs, trapped behind an interface that only spoke the language of graphics. A few academic teams tried to hack around this limitation anyway. They disguised their calculations as graphics operations, just to steal the raw horsepower, a workaround that was clumsy, fragile, and required deep specialized knowledge most scientists simply didn't have. It worked technically. It also made it obvious that there was a real opportunity sitting untouched. In 2006, Nvidia made a decision that looked at the time almost unnecessary. It released CUDA, a platform that let developers write ordinary code and run it directly on the GPU without disguising their calculations as graphics work. This wasn't a driver update or a small utility. It was a compiler, a runtime environment, a set of programming libraries, and a full toolchain for writing, debugging, and optimizing GPU code. Nvidia was building an entire operating layer on top of its own chips, essentially teaching the rest of the software world how to speak to hardware that had, until then, only understood pixels. For years, this looked like a bet with no clear payoff. Gamers didn't care about general-purpose computing. Wall Street didn't care. Nvidia's stock and reputation still rose and fell almost entirely on how well its cards ran the newest games. Most of the company's revenue came from selling cards to play video games, not to run scientific code. Building and maintaining CUDA cost real engineering time and real money for a market that, on paper, barely existed yet. But researchers in obscure corners of computer science, the people quietly training early neural networks, long before deep learning was a term anyone outside academia recognized, started using CUDA because it was the only practical way to make their models run fast enough to be useful. Training a neural network on a regular processor could take weeks. On a GPU using CUDA, the same training run could take days or even hours. That kind of speed up doesn't just save time. It changes what's possible to try in the first place. Ideas that would have taken a career to test could now be tested in an afternoon. That's the part most viewers miss. Nvidia wasn't reacting to the AI boom. It spent almost a decade building the foundation before the boom existed, with no guarantee it would ever pay off by the time deep learning exploded into public awareness. The moment usually pointed to is 2012, when a neural network trained on Nvidia GPUs dramatically outperformed every other approach in a major image recognition competition. The tools were already sitting there, refined, documented, and battle-tested. By years of quiet academic use, libraries for fast matrix multiplication, optimized routines built specifically for neural network layers, a compiler that squeezed extra performance out of every new chip generation without forcing developers to rewrite their code from scratch. When AI researchers around the world suddenly needed hardware that could train much larger models, CUDA wasn't a new option they had to evaluate from zero. It was simply the default, because nobody else had spent a decade quietly building anything comparable. This is where the real advantage starts to show, and it's also where most explanations of Nvidia's success stop too early. A rival company can design a GPU that matches or even beats Nvidia on raw specs, more cores, more memory bandwidth, better power efficiency. On paper, that part, difficult as it is achievable. Chip design is hard, but it's a known problem with known engineering solutions, and several companies have gotten close. What's far harder to replicate is everything sitting on top of the chip. Think about what actually has to happen for a machine learning team to switch away from Nvidia hardware. Every library they rely on has to be rebuilt or reworked to run on the new platform. Every optimization that engineers spent years tuning for one architecture has to be redone from scratch, often by trial and error, because the new platform behaves differently in ways that aren't always documented. Every engineer who has spent years learning one set of tools, one set of debugging techniques, one set of performance quirks has to relearn a different system with different bugs and a much thinner base of tutorials, forum answers, and institutional knowledge to draw on. Multiply that friction across thousands of companies, universities, and research labs, all making the same calculation independently, and you start to see the actual size of the wall competitors are climbing. It helps to picture this as a stack of layers, because that's really what it is. At the bottom sits the physical hardware, the GPU itself, the transistors carrying out the raw computation, the silicon that gets most of the public attention. Just above that sit the drivers and low-level libraries, the software that translates human-written code into the exact instructions the chip circuits understand. Above that sit specialized toolkits built for specific jobs, deep learning primitives that speed up common neural network operations, math libraries tuned for particular kinds of calculations and communication, tools that let thousands of GPUs coordinate together inside massive data centers, which is exactly what training today's largest AI models requires. And at the very top sits the layer most engineers actually interact with day to day, the AI frameworks that let someone define a neural network in a few lines of readable code without ever touching the layers underneath. Every one of those layers for close to 2 decades now has been built and continuously optimized specifically around Nvidia's platform. That's the trap facing any competitor. They're not just being asked to build a competitive chip. They're being asked to rebuild an entire stack, convince a global industry to relearn its tools, and do all of that while Nvidia keeps shipping new hardware generations that stay compatible with the exact software investment developers already made years earlier. A model trained with CUDA tools 5 years ago still benefits from updates today. With minimal rework, that continuity is itself a product, even though nobody sells it separately on a spec sheet. It isn't as though rivals haven't tried. AMD has invested heavily in its own alternative software platform, aiming to give its GPUs a comparable programming environment. Intel has pushed its own open computing effort, trying to build a standard that isn't tied to any single company's hardware. Both are real, serious engineering efforts, backed by companies with enormous resources. And both have struggled with the same core problem. convincing developers to spend time porting code and rebuilding institutional knowledge for a platform with a smaller user base, thinner documentation, and fewer already solved edge cases. Developers tend to go where the existing code, the existing tutorials, and the existing colleagues already are. That creates a loop that reinforces itself. More users produce more documentation and more fixes, which attracts more users, which is precisely the kind of loop a decade-long head start is very good at winning. Universities added another layer to this cycle without ever intending to. Because CUDA was the practical tool available during the formative years of the deep learning boom, it became what students were taught in courses and used in research projects. Those students graduated into industry roles already fluent in one platform and unfamiliar with the alternatives, which meant the companies hiring them inherited the same platform preference by default, generation after generation. Even the newer AI frameworks that abstract away most of the low-level detail, the tools that let a researcher write a few lines of high-level code without thinking about the hardware underneath at all, were themselves built and most thoroughly tested against Nvidia's platform first. In theory, that abstraction layer could someday make the hardware underneath interchangeable, letting code run equally well on any company's chips. In practice, years of deeper optimization work on one specific platform means that even code written in a supposedly hardware-neutral framework often runs meaningfully faster, with fewer strange bugs, specifically on Nvidia hardware. The abstraction promises neutrality. The performance gap underneath quietly undermines it. Every year that passes, the amount of code, published research, trained engineers, and institutional knowledge built on top of CUDA grows larger. Switching costs don't shrink over time as the technology matures. They compound. The same way a language spoken by more and more people becomes harder for any single alternative to displace, no matter how logically designed that alternative might be. This is also why the story isn't really about chips at all, even though chips are what get photographed and benchmarked. It's about standards. Whoever controls the software layer that developers build their work on top of ends up controlling which hardware sells, almost regardless of how good the alternative hardware actually is on paper. A better GPU sitting behind an unfamiliar, thinly documented software environment loses, again and again, to a merely good GPU backed by a decade of tools, tutorials, and trained engineers. That's not fundamentally a hardware story. It's a platform story, and platforms are some of the hardest competitive advantages to dislodge once they take hold, because unseating them requires beating not just a product, but an entire accumulated habit of an industry. There is a financial dimension to all of this that rarely gets discussed alongside the technical story, and it changes how you should think about Nvidia as a business rather than just as a chip designer. Selling hardware is a transaction. A customer buys a GPU, and once the sale is complete, nothing obligates them to buy the next one from the same company. Selling a platform is different. Once a company, a research lab, or an entire university curriculum builds its workflow around CUDA, every future hardware purchase becomes less of an open evaluation and more of a renewal. The software isn't just a feature that helps sell the chip once, it's a recurring reason to keep buying from the same vendor generation after generation, without ever charging a separate subscription fee for it. That's a much more durable kind of business than hardware sales alone would ever provide, and it's part of why Nvidia's profit margins have stayed so much higher than a typical hardware companies, even as competitors have closed much of the pure performance gap on paper. It's also worth being precise about where this advantage does and doesn't apply, because the picture isn't uniform across The entire industry. The very largest technology companies, the ones running some of the biggest data centers on the planet, have both the money and the specialized engineering teams needed to build custom chips of their own, sometimes paired with custom software written in-house specifically for their own workloads. A handful of these companies have done exactly that, training some of their models on hardware that never touches CUDA at all. For an organization with thousands of engineers and total control over its own software stack from top to bottom, the switching cost that stops everyone else is something they can absorb. That's the exception that actually proves the rule. Only the very largest, most resourced players can afford to root around the platform lock-in, while everyone else, every smaller company, every university lab, every independent researcher finds it far cheaper to simply stay on the platform that already works. That asymmetry matters for how you should picture the market going forward. It isn't a single battlefield where one winner eventually takes everything. It's closer to two separate contests happening at once, among a small number of giants with the resources to build their own full stack, real alternatives to Nvidia's platform already exist and are being used today quietly without much public fanfare. Among everyone else, the vast majority of companies, labs, and individual developers actually writing AI code around the world. The software layer still overwhelmingly favors the platform with the decade-long head start, simply because rebuilding that much accumulated tooling and knowledge from scratch isn't a realistic option for an organization without enormous dedicated engineering resources. None of this makes Nvidia's position permanent. Regulators in multiple countries have started paying closer attention to exactly this kind of software lock-in, asking whether a hardware company controlling the dominant programming platform for an entire industry raises the same competitive concerns that software monopolies raised in earlier decades of computing. Open source efforts keep chipping away at the problem from different angles too, building translation layers that let code written for one platform run, with some performance cost, on another, hoping that enough collective engineering effort can eventually make switching platforms less painful than it is today. Some of the largest AI labs have started quietly investing in these translation tools themselves, less because they expect to abandon their current hardware immediately, and more because having a credible alternative gives them leverage in future negotiations. Even if they never actually use it, history offers a quiet warning of its own here. If you look at how other dominant computing platforms have eventually lost their grip, they rarely fall to a single better competitor arriving all at once with an obviously superior product. Entrenched platforms tend to erode slowly from unexpected directions, a shift in what kind of computing problem matters most, a new generation of tools that quietly routes around the old bottleneck, a slow accumulation of just good enough alternatives that finally makes the switching cost stop being the deciding factor for enough people at once. It rarely looks dramatic while it's happening, and it's usually only obvious in hindsight, years after the shift actually began. So the next time someone credits Nvidia's dominance purely to cheap design, remember what's actually running underneath the silicon. The transistors matter, and they matter a great deal. But the real moat was built years earlier, quietly, layer by layer, in a software platform that almost nobody outside a handful of research labs was paying attention to at the time.